Hello and welcome to IPSec eLearning web class. This discussion will cover network security fundamentals. Now, for everyone's information, IPSec training offers e-learning sessions on a weekly basis. We conduct 3 web classes every Wednesday with topics ranging from Internet Resource Management, IPv6, routing, DNS, and network security. Of course, you are most welcome to look at the schedules on our website. That's at training.ipsec.net, and register for topics that you find interesting. Now, before we proceed, allow me to first introduce myself. My name is Cheryl Hermoso. I am working as a training officer with IPSec. IPSec stands for the Asia Pacific Network Information Center, which is the regional internet registry for the Asia Pacific region. Now, as part of the training team, we deliver workshops and training courses to the members of the internet community around the Asia Pacific region. Now, of course, to supplement these training events, we also offer e-learning courses such as this, which will be easily accessible for everyone. Now, prior to IPSec, going back to my background, I was also a network and systems engineer for a big academic institution. Now, that's a bit of a background about myself. Now, let's begin the class. Before we look into this diagram, I'd like to give you a brief overview of what we will be covering for this session. Now, this e-learning course aims to provide you with a sufficient knowledge about the key concept, key aspects of security. We will cover key concepts, protocols, and possibly some policies involved in establishing a secure network. We will look into network and infrastructure security from a layered perspective. We will also see some form of attacks and different ways in which we can mitigate them. So that's what we want to cover. This is an introductory course. There is an assumption that you have some fair amount of background about TCP/IP and networking in general. Now, going to this session, we will first begin with a discussion of the goals of information security. What is our goal? Our goal, of course, is data protection. We have certain information that we want to protect. As such, we refer to this as information security. Now, to achieve this goal, we present these 3 core principles of network security, or generally you can say information security as well, and it's also known as the CIA triad: confidentiality, integrity, and availability. Now, let's discuss each of them. There are different types of data. There are different types of information. Some are available to the public, while more sensitive information are kept private or classified, right? They are limited only to a number of people. In short, we want some things to be confidential. So that's the first goal here. We want some things to be kept confidential. So when we say confidentiality, it ensures that information can't be accessed by anyone without having any proper authorization first. This means that we have some form of control access. If we're transferring data, confidentiality also tells us, it also provides us an assurance that the information can be read only by the intended recipient and not by any third party if ever it's intercepted while being in transit. So that is confidentiality. It prevents any unauthorized use or disclosure of information. That's our first goal. The next one there in purple is integrity. Integrity refers to the accuracy and the completeness of information. The data that we receive must have the same meaning as the data that was sent to us. So in short, it just ensures that any unauthorized users won't be able to modify our data. It means that the data has not been altered in transit. Whether it's intentional or not, we want to make sure that we're still getting the same information from the sender going to the destination side. So integrity, our meaning for that is it safeguards the accuracy and the completeness of our information. The last one is availability. Now, availability ensures reliable and timely access to information whenever or wherever we need it. What does this mean? It means protection against any type of disruption and any type of attack that will possibly cause our information or our service to be unavailable to our users for unspecified amounts of time. We want our services to be up and available for our customers at least 99.9% of the time. So those are the three goals. Availability there says authorized users have reliable and timely access to information. So what we want to see here is that these are the core principles of security. As we move on and discuss more detailed protocols and implementations, keep in mind that they are a means to meeting these goals and these principles. Okay? So the next slide covers just a fair background of why do we need security. I think you're very aware of this by now. I think you know that. That's why you're coming into or listening to this class. Why do we need security? Well, of course, the internet that we know nowadays is very different from what it was in the early days. Initially, the internet was designed for connectivity. So there is a trust assumed amongst the networks or amongst the different hosts that are connected to ARPANET at that time. Nowadays, we do more with internet. We use it for internet banking, we use it to send our personal information, we use it to communicate. So the way we use it nowadays is very different from the way it was being used or its intended goals at the start. So we had TCP/IP. TCP/IP is basically the protocol that we use for running for basically sending network data or network packets. But security protocols have now been added on top of TCP/IP, whereas originally it's bare bones. It doesn't have much security in place. Now security has been added onto the different layers of our TCP/IP protocol suite. Now there are fundamental aspects of information, of course, that we need to protect. That is our goal, to protect our data. What are these types of information? Possibly your confidential information, your records, your employee records. Possibly for your businesses, you have your business models, okay, intellectual property, or you just want to provide protection for your employees' identity and also for your resources. So that are some of the fundamental aspects of information that we want to protect. And of course, as you know nowadays, everything is connected on the internet. We can't really keep ourselves isolated from the internet. Most businesses communicate using online transactions. We also may be providing websites or even services that are online to our customers. Or we may be using other third-party or other companies and get their services online as well. Therefore, what I want to say here is that the internet has been a key, it has been a useful tool for businesses, for organizations, basically for everyone, not just to connect, but also to do all transactions over the internet. Okay, so we need some form of protection because we can't really isolate ourselves from the internet. So let's look at the attacks on different layers. When we say network architecture, there are two major models that describes its nature. Of course, one is the OSI model and the other one is the TCP/IP model. These models basically define the architecture of networks from an abstraction layer point of view. The OSI reference model, it's a layered model of the network architecture. It uses abstraction layers to subdivide the different communications process in terms of their functions and also the protocols that are operating in each of these layers. Now, there are 7 layers in total, as you can see in this diagram. We have application, presentation, session, transport, network, data link, and physical layers. So as data is being passed from the top going down to the bottom layer of our infrastructure, basically it's going down to the lower layer next to it. Data is being passed from top going down, and this data will become the payload to the lower layer. It will be passed on downstream until it reaches a point where it will be passed on the physical layer on different physical media, such as maybe cable, wireless, fiber, and so on and so forth. So that is not our goal here. I assume that you already know that by now. So I just want to give you a brief background about the reference model because we will look into the attacks from these different layers. Now, just a bit of a discussion on the TCP/IP model as well, just to have some comparison. This is the equivalent TCP/IP protocol stack on your right. So I'll use my laser pointer there. So basically, the TCP/IP model is a more descriptive framework. It has 4 abstraction layers instead of 7, which is meant to describe how data is formatted, routed, and transmitted. So basically, it's the same, just smaller layers, and it's more descriptive into how actually it's being manufactured by vendors nowadays. Now, we'll not explain the functions of each layer in detail. Suffice it to say that the layered functionality is based on 2 things: its function and, of course, the protocols that are operating in each layer. Now, the diagram shows the view of security threats from the layer perspective. Each layer is prone to attacks, right? As I've told you in the previous slide, okay, TCP/IP doesn't have much protection in itself, but protocols are defined, protocols came up, are implemented on top of the TCP/IP as time moves on. So let's have a look at these different attacks. See here, these are the protocols that are running on each of the different layers. Now, in our discussions, let's look at the OSI reference sites because it's easier to look at it like just calling the different layers. So basically, these are the different protocols. You have PPTP token ring from layer 2. You have IP, ICMP, and IPSec in layer 3. You have TCP and UDP on layer 4. And all the way to the top in layer 7, you have the different applications: DNS, DHCP, HTTP, Radius, Telnet, SNMP, LDAP, and so on and so forth. So there are plenty of different protocols running on different layers. So you should be aware which layer your protocol is running so that you will know how to protect each of them. Now, these are some of the attacks that can happen in these layers. I'm pretty sure you've heard about ARP spoofing, MAC flooding. It occurs on the lowest layer, okay, or on top of the physical, which is on data link layer. You also have ping floods, ICMP floods, TCP attacks, routing attacks, and SYN floodings all occur in layer 4. And on your layer 7, there are heaps of these different attacks. Some of the more common ones are DNS poisoning, phishing, SQL injection, spamming, scamming, and there are many others that you can find out there. So basically, these are the attacks. And let's have a discussion of some of these attacks in here. So first one, let's look at TCP attacks. What is TCP in the first place? TCP stands for Transmission Control Protocol. It provides reliable and ordered delivery of packets between your hosts. TCP is, we can say that it's a connection-oriented protocol, meaning it must first establish a connection between your host and the server, okay, or the client and the server, and then before they can send and receive packets to each other. To do this, a client will initiate what we call a 3-way handshake. Now, this here is the client, okay, and we have a server on the other side. So basically, your client will start the 3-way handshake by first sending a SYN or a synchronized signal. That's the very first command. Then the second response will be a SYN command and an acknowledgement command. SYN-ACK will be from your server. And then finally, the client sends a final acknowledgement. And from this point forwards, since both of them have acknowledged each other, the connection is established and they can send and receive packets from each other. Now, how does TCP attacks occur? So it actually exploits the TCP 3-way handshake. So what happens here is, if you can have a look at this diagram here, we have our attacker now. So this is still a client server setup. So but our client now is like an attacker. He wants to overwhelm, he wants to send a TCP attack to the server. So TCP attacks or SYN flooding is a type of a denial of service attack. It's a DOS attack. The attacker exploits the 3-way handshake by sending a succession of SYN requests. It floods the source or the server with hundreds of these SYN packets. Now the server will also still send a SYN-ACK, right? That's the second point. So her attacker here will send plenty of different SYN requests. The server will still reply with all its acknowledgements for each of the SYN requests being sent by the attacker. Now, however, what's missing here is the final acknowledgement. Now, since the attacker purposely sent out the SYN requests, he also purposely doesn't want to acknowledge each of them. So what happens is you have this finite queue size for incomplete connections, and the attacker is trying to use up all of them. Once the queue is full, the server doesn't accept any more requests, even if those requests are coming from legitimate sources. So if you have a legitimate client somewhere on the internet also trying to access the same server, he won't be able to do so. So that is TCP attack. It seems like a very simple attack, but this has been happening, this has been occurring a lot over the past few decades, a few years. Okay, let's discuss about DNS cache poisoning. Before, in the previous slide, we discussed about TCP attack, which is on layer 4. Now let's move up all the way to layer 7 and discuss DNS cache poisoning. Now there are many forms of attack that are focused on the applications. Why is that? It's the easiest one. It is the one that's interfacing with us automatically, right? So there are many different forms of attacks that's happening on the application layers. Most of them are either concerned with those that don't authenticate properly, or those probably that are sending clear text authentication, such as, let's say, FTP, Telnet. Those are very easy targets for attackers. Let's take DNS as an example here, because DNS is one of the critical infrastructure that we need for the internet to properly basically function smoothly. So let's look at DNS cache poisoning, which over the past 4 or 5 years has been one of the major problems within DNS. So DNS cache poisoning is illustrated in the following diagram. We have again a client who wants to connect to a server. Let's just say that it's a web server. So it's trying to connect to www.example.com. Okay, so it's a primary server. Okay, so this client will now try to access www.example.com. He sends a query to the primary DNS. So that is how this DNS server will also act as a caching or a recursive server. It will query the DNS hierarchy tree. It will query the root all the way to the top level domain and subdomain until it reaches the authoritative server that can give the IP address that he's looking for. So basically, client is asking for the IP address of example.com, the web server. So this is how it works. It sends the DNS recursive server will send the query to the root all the way until it reaches the authoritative server, which is ns.example.com. Now what happens here is for every query that is being sent out by your recursive server, it has a corresponding query ID. Okay, so any query, so that when I receive a reply, so let's say this authoritative server now has the answer to my question. The IP address that you're looking for is 192.168.1.1. So I will reply with the same query ID which matches the query ID of my requests. After that, this DNS caching server can now reply to the client and give the same answer. Okay, so that's basically how DNS works. Now looking at a possible problem, which is cache poisoning. Let's just say that somewhere here we have a malicious user who wants to poison our caching server. It is pretending to be the authoritative server. Now the result is that the query for a domain will now return an IP address of a bogus server instead of the intended domain. Okay, so this will try to be an authoritative server. He will send a reply. Notice here that the reply is pointing to 192.168.1.99, which is essentially not our proper web server, which is this one. All right, so he will send a succession of these replies with different query IDs. Now, one of the problems with the early versions of DNS, and if you haven't configured your servers properly, is that query IDs are sequential. Okay, so it exploits this problem. All these query IDs, it's a unique identifier that is associated with all the query packets that are and reply packets that are being sent out. Query IDs are sequential and therefore they are predictable. So when the victim name server sends the query packets, the attacker will just basically flood the victim with reply packets containing the forged IP address for example.com, hoping that at least one of them, of course, will match. As you can see here, we found a match. So when that happens, this DNS caching server will accept the reply packet because it's matched with the query ID and give the wrong information to this client. Now, of course, this authoritative name server will still reply, but it will be just a race between this reply and this reply. If the correct reply arrives at a later time, so more latency, therefore, since the DNS caching server already has a reply, this correct reply will now just be discarded. Okay, so that is how DNS cache poisoning will work. Okay, so most of the attacks that are mentioned above that we've discussed uses a combination of these common attack types. It usually begins with reconnaissance, or basically finding vulnerable systems over the internet. We can do ping sweeps, we can do port scans using several different sophisticated tools that are readily available for us. It likewise identifies all hosts, devices, and services on the network, their operating systems, the vulnerabilities that are possibly associated with them. And of course, having this information can be scary. Okay, so first one, ping sweeps and port scans can give us a lot of information. That's why it's called a reconnaissance attack. We only need to get information first before sending, okay, a more active type of attack. Once the attacker has access to the network, he can capture packets as they pass through the network. Is that right? He can do sniffing. He can do eavesdropping. Sniffing, eavesdropping, they are a form of data interception attack. The process is very simple. They can just perform this using a hardware or a software that's also readily available. Then it will just listen to all the messages that are being sent through in the network. If in some way, perhaps someone is sending a password on a clear text, then he's very unlucky for that day because someone else has got access to that. It can be used to access his device, or maybe he's using the same passwords all over the network. Then it will be used for to gain access to those things. Next one is man-in-the-middle attack. Now, man-in-the-middle is more of an active form of eavesdropping. The attacker intercepts messages that are intended for a valid device, then it will inject new ones. Okay, so it's like you have something in the middle, the sender and the destination both think that they're talking to the same person, whereas your message actually may already be distorted because of the man-in-the-middle attack. Another one is spoofing. As we've seen, spoofing, basically you're setting up a fake device and you trick others to send messages to that fake device. So you can see this if you know about ARP spoofing. This can be best demonstrated with an ARP spoofing attack. You also have denial of service, or DOS, and distributed DOS or DDoS, which are attacks that generally seek to make a computer or a server or maybe a network or a service unavailable to its users. So DOS and DDoS attacks, they happen almost every day, or perhaps really every day. For servers serving a large audience, the attacker sends out large traffic to overload the server. So what do we do? So you can see all these different possible attacks. What do we do? How can we be proactive about these things? How do we protect our network? Now, an answer to that can be these two things. First is we can have a defensive-oriented technology. That's most of us use this as our point of protection. The vast majority of networks today are secured using these. These technologies are of course required, but as you can see later on, they're no longer enough to fully manage the security of an organization. So the primary defensive technologies include firewalls, intrusion detection systems. Firewalls is usually our first line of defense from threats that are occurring outside of our network. Intrusion detection is another good way of preventing or defending our network. It's usually our second line of defense. You can have an IDS appliance or a software or an application that can look for known vulnerabilities or patterns that can be used to break into your system. Now, using these two will make it more difficult for attackers that are outside of your network. Okay, that's why it's like you're protecting the perimeter of your network. However, most attacks nowadays can also come from within, from our internal network. Okay, so for attackers that are within the internal network, make sure that you have other forms of security in place. Now, this other way that I'm referring to is building trust on top of the TCP/IP infrastructure. We're integrating trust in the security infrastructure, which requires us to have some form of authentication. Okay, and perhaps we can also implement public key infrastructure. Now, the first one, strong authentication, is an absolute requirement. It's a must. More specifically, we need a strong multi-factor authentication. I'm sure you've heard about two-factor authentication nowadays. It's basically a combination of something you know, a PIN or maybe a password, and something that you already have, a token. Now, a classic example for this is the ATM machine. The token is your actual ATM card, and you must also give a PIN, right? Which only you should know about. Another example that you may have noticed is most or a lot of the big website providers or application providers are also using two-step verifications, where you can download an application onto your phone. When you log into these websites, you still input your usual username and password, and after that it will ask for a verification code, which will be generated. It changes let's say every 60 seconds on your phone, and you have to input the correct verification code before you can actually have access to the system. Okay, now the next one is public key infrastructure, or PKI. PKI, it typically spans a whole range of other technologies. It involves digital signatures, it involves public keys, private keys, certificate authorities. But broadly speaking, when we talk about PKI, it's like establishing a web of trust. We have a third party, a trusted third party, also known as the certificate authority, which verifies that an individual or maybe a company, okay, is actually who they're saying they are by issuing them a digital certificate. Let's look at access control. What is access control? So we've talked about strong authentication. So it's one way of having an access control. An implication of having authentication is having to restrict access to our data. That is done using access control. So generally, when we say access control, it's the ability to permit or deny the use of an object by a subject. It introduces three essential services, three important words that we always refer to when we talk about network security, which are authentication, authorization, and accountability. Okay, so we also know them as collectively as AAA. Identification and authentication would normally come hand in hand. So the first one here, authentication, answers the question, who can log in? Who are allowed to log in onto your system? Now, as I've said, identification comes prior to authentication and they come hand in hand. Identification is where let's say I'm the user who wants to be authenticated. I come in and proclaim myself. What's my name? What's the password that I know? And I present that to an authentication mechanism. The authentication mechanism will now try to verify the identity. So when you log in, before you enter an event or a website, you introduce yourself, you tell the username and password, and an authentication system will tell you whether your password matches what they have on the system. That is authentication. The next one is authorization. So basically, once you're into the system, okay, the next step is authorization. Authorization defines the user's rights and permissions on a system, what an authenticated user can and cannot do within the system. So going back to our example, let's say you already have access to the system. What are your limits? What are the things that you can do while you are in the system? Are you limited only to access certain portions of the folder? Or maybe you can edit, make changes, delete, and add files onto a folder, things like that. So that is authorization. The last one is accountability. Accountability basically just tells you or identifies what you did while you were on the system. Okay, it's an audit trail. It's a form of logging, a record of all the activities or actions that are associated with the user that is logged in. So make sure that you know all these three: authentication, authorization, and accountability. They are basic terminologies that we use a lot in network security discussions. Now let's look into cryptography. Cryptography is a major part of security. That's why we need to really cover this in detail. We will have other types of e-learning that covers only cryptography, but for now we will look at it from a broader perspective. So what is cryptography? It's an old method of making messages undecipherable. It's a means of protection. Let's say when you have information or data or maybe just a simple message, when it falls into the wrong hands, just make sure that these third party cannot read or cannot understand what's written on that message. So from that definition alone, you can see that there is a very big potential of using cryptography in the security field. Okay, and as you know by now, it has evolved into this very complex science or field in the information security. Our definition of cryptography has the line making messages undecipherable. Now this is achieved using encryption. Okay, encryption is the process of transforming a plain text into a ciphertext using some form of cryptographic key. So we've introduced three terminologies there. You have a plain text, you have a ciphertext, and you have a cryptographic key. So these are three important terminologies. A plain text basically is your data, your original data in its original readable format. The plain text will be transformed into a series of scrambled letters, characters that we now can call a ciphertext. This transformation is performed using an encryption algorithm, okay, such as maybe DES, 3DES, AES, if it's symmetric, and many other forms of encryption algorithms that are being introduced or that are available on the market now. Okay, so data encryption can be done either on a single fixed size or a block, or it can be done on real time. I don't have the slides for that, but basically we have two types: block cipher and stream cipher. Block cipher is if it operates on a single fixed block to produce the corresponding ciphertext, or if you talk about stream cipher, it operates in real time on continuous streams of data. Encryption can also be either end-to-end, okay, where you have your packets encrypted from your source and then decrypted on the final destination. It can also be link encryption, where you encrypt and decrypt your data at each node. So if it passes through several stages of routers or different nodes, then at each point it will be encrypted and decrypted all in each of those hops. This is a very simple diagram of cryptography, so which is we've already defined in the previous slide. So you have here your plain text, okay, and this plain text will be converted into a ciphertext, okay, after it passes through an encryption algorithm. Once it reaches its destination, this ciphertext will be converted again onto a plain text so that it can be read in the destination, and it passes through what we call a decryption algorithm. So it's a series of encryption and decryption. So let's have a discussion of the two major types of cryptography. We have symmetric key cryptography and asymmetric key cryptography. So as you can see here in this diagram, we have an encryption key and a decryption key. This is actually an example of symmetric key cryptography where you have the same key for both encryption and decryption. We also call this cryptography type as a shared key cryptography because this key has to be shared by your source and your destination for them to be able to decrypt the message once it reaches its final destination, right? So you are basically sharing the same key. Now, how to pass on or how to transmit the key from your source to your destination is left for you to do. Make sure that it is done securely. You can use secure protocols. You can use it, do it manually. It depends on you. But basically, that is symmetric key cryptography. The second one is asymmetric key cryptography. So the difference between these two is that asymmetric key uses two sets of key. You have a public key and a private key. So what are some of the examples where we use cryptography? Well, there are common ones that we know of. I'm sure you've used it some way or another. We have digital signatures, message digests, and of course, public key infrastructure. So I think I have some slides here that discusses all of them. So let's look at public key infrastructure or PKI. So basically, public key infrastructure is not just one protocol. I have a bit of discussion of that in the previous slides. Basically, it's an architecture, it's an infrastructure. It's a combination of different things, hardware, software, even people and organizations, even policies and procedures. But the main goal of PKI is basically to ensure or to enable users of a public network to securely exchange data using public and private cryptographic keys. Okay, so as you can see, PKI, when you talk about digital signatures and all that, we are using asymmetric key cryptography. Okay, so digital certificate is the basic element of a PKI. We have a certificate authority. So see here, these are the components. You have a certificate authority, a registration authority. These CAs and RAs will have a repository for all the current or active digital certificates. And we have an archive for all those that are expired and revoked certificates. Okay, so the basic element of a PKI, as I've said, is the digital certificate, and it is issued by a certificate authority. So of course, the CA will have to verify whether the organization or the person requesting for a certificate is actually valid, or the names or the everything basically that he said about himself is true and it's verifiable before the CA digitally signs these certificates and give to the customer. Okay, so basically that's what happens here. When you have a very big CA, they can have a different registration authority. If it's a smaller CA and RA can have the same function. What is an RA? RA is a registration authority. It's the arm that basically verifies registrations that are made to them. If, let's say, I'm claiming that I am the representative of this company, then it is the job of the RA to verify that they gave them the correct information before giving me the digital certificate. Okay, as I've said, if you have smaller CAs, these RA should be part of the CA itself. Okay, so from what we have covered, we've seen the slide in it previously. We've seen that attacks happen on each layer of the OSI model. Some protocols have been devised to counter-attack or to mitigate these threats. So what are these ways? So notice I've changed it to blue ones. So these are some of the protocols that we can implement on our systems to fight or basically to combat the threats that are happening. So to name a few, we have the IEEE standard 802.1x, you have VPN protocols, PPP, PPTP, and maybe IPSec on the network layer. You have TLS, SSL, and SSH on the transport layer. And on the application layer, you have HTTPS, DNSSEC, PGP, SMIME, and a whole lot of other security things as well. Let's discuss IPSec, or let's discuss more generally, let's discuss VPN. What is VPN? VPN is Virtual Private Network. In the early 90s, network for large organizations and enterprises basically use or connects to each other through what we call leased lines. VPN, or Virtual Private Network, creates a secure tunnel over a public network. So you no longer need leased lines, because leased lines are very expensive. Instead, you are using the public internet but still maintain the secure connection between these different remote offices or remote sites. You have a tunnel that's created by either encrypting or encapsulating the data that is transmitted across your VPN network. Common application of VPN, of course, is if you have you're establishing remote connections between different offices, or if you have clients or employees that are remotely connecting to the office network or work network whenever they're away of the office. Okay, think of it as, like, say you have two islands. So instead of creating a bridge to connect these two islands, sometimes it is more optimal to just use a public bridge. You still keep your data private because we are using tunneling. Now, these are the different VPN protocol standards. You have PPTP, L2F, and L2TP, which operates basically on the data link layer. PPTP was developed by Microsoft and was commonly used to secure dial-up connections. It operates in the data link layer, as I've said. At the same time that PPTP is being introduced, Cisco was also developing their own version, which was called L2F, or the Layer 2 Forwarding Protocol. So, which basically, in function, there might be a bit minor differences, but essentially they're the same thing. Then, at some point in time, IETF created a standard which combines these two and called it L2TP, or Layer 2 Tunneling Protocol. The last one is IPSec. IPSec is the current standard for VPN implementation. It operates on the network layer. It's not operating on the data link layer anymore. So it operates on a network layer, and it's commonly implemented on routers. Okay, so a bit more discussion about IPSec. So when we talk about IPSec, where is our concern? It's here. It's network layer, so typically router to router connections. IPSec, or IP security, is the means by which the IP layer, or layer 3, is given security. IPSec can provide protection for common communications, that is either end-to-end or maybe node-to-node, one computer to another computer, or it can also provide protection from one network to another network. There are two modes in which we can we operate IPSec, either tunnel mode or transport mode. In tunnel mode IPSec, the entire IP packet is encrypted and becomes the data component of a new and larger IP packet. The new IP packet has a new IP header, of course, and an IP header. So you're basically creating a larger IP packet in tunnel mode. In transport mode, the second one here, where we are not introducing a new packet, we're not creating a new packet. Instead, the IPSec header is inserted in between the IP packet and between the IP header and the payload. So it's inserted somewhere in your IP packet. No new packet is created. IPSec is actually a combination of different protocols. It's a suite of protocols, and it can be fairly complex. So the IPSec architecture combines these different components: security associations, authentication headers, or AH, encapsulating security payload, or ESP, and Internet Key Exchange, or IKE. All of these components, all of these protocols are brought together to provide layer 3 security. They have their own RFC, so if you want to have a detailed understanding of IPSec, you may have to read a lot of different standards all about the different components of IPSec. A security, ISEC-KMP, the Internet Security Association and Key Management Protocol, it's a system that defines how your VPN server and your VPN client will have or will set up their security associations. So it's a key management protocol. IPSec has been fully supported in many equipment and operating systems nowadays, such as if you have Cisco IOS, if you're working with Juniper OS, if you're working with different operating systems such as Mac OS X, BSD, Linux, or Microsoft, all of them have support for IPSec nowadays. So it's very common, it's very easy to set up IPSec and to secure any IPv4 traffic. Moving up a bit on our different layers, so let's talk about layer 4. What are the different security protocols there? We have TLS and SSL mostly. TLS and SSL encrypt the segments of network connections above the transport layer. It uses symmetric cryptography. It's using that for privacy. It's also using a keyed message authentication code, or HMAC, for message reliability to prevent any eavesdropping. TLS is an IETF standard, so don't get confused between SSL and TLS. TLS is basically the implementation is the standard version of SSL when SSL became version 3 and IETF decides to standardize these things. Okay, it succeeded eventually the SSL operations at the transport layer, and it's independent of any application protocol. The current version SSL 3.0 is what we are now called TLS version 1. It was standardized in 1999. Establishes a stateful connection using handshake procedures after negotiating some parameters. So that's how TLS or SSL actually work. Now you may be aware, you may be familiar with SSL when it's being implemented in conjunction with different application layer protocols such as HTTP. We have secure HTTP, which is the secure implementation of HTTP by using SSL to encrypt these communications. Okay, so it's just two of these protocols combined together. So you still have normal HTTP connections, but on a lower layer, on your layer 4, you use SSL to encrypt communications, okay, and secure the identification of your web server. The trust, again, will be based using inherent trust, using certificate authorities, okay, and also the most commonly seen applications of these are also, let's say, not just web browsing, it can also be used in emails, in VoIP, in SSH, and all that. So just wrapping up the security discussions, let's look at security management. Here are some operational security thoughts that I'm sure most of you are already aware, but it's always worth checking again and reminding people about it. Network security is only one layer of a bigger information security plan. So having a one-time, well-designed infrastructure is never enough. It is never enough. Vulnerabilities are discovered every day, and you have to make changes on your information security plan from time to time. In most cases, it should be on a regular basis. As an organization, everyone from end users to system administrators to network engineers to the employees are responsible for keeping the security. As we always say, an organization can only be as strong as its weakest link. Okay, an organization must have also a well-defined policy structure. All entities in the organization, including users, IT admins, even managers, will be responsible for maintaining the integrity of the system. Okay, so therefore, you must develop and implement a comprehensive information security policy. When we say policy, these are aimed at informing our users as well as maybe lay out the baseline for our security. The other thing is standards. Based on our policies, we can create standards. We can set up these standards, including, let's say, for example, the use of specific technology in a uniform way. For example, we'll be using the same type of software, same antivirus, same desktop firewalls for all our end users, so that it can improve our efficiency. It's easier for us to secure because it's usually mandatory and we only have to be familiar with that system. It accomplishes consistency and uniformity as well. Now, these are some of the things that you can do in order or you can include actually on your comprehensive security plan. Passwords, something that's very important. Specify what password rules will you implement if you want to regularly change the password, if you have a minimum requirement for your password length. All of that should be included in your security plan. Now, the third one in this list here is guidelines, which we haven't discussed yet. When you say guidelines, these are not mandatory, so it's not like standards, but these are best practices that we can tell our users. Okay. Lastly, your organization must have a disaster recovery and attack mitigation plan. You always have to plan for the worst. This is part of the big information security plan that you will create, of course, and you will update from time to time. The last part of our discussion is on Whois Database. What is the Whois Database and why do we need that here? The Whois Database is essentially just a public record of all the network resources, IP addresses, routes, IP address allocations, different contacts that are responsible for these resources are all listed down in the Whois Database. How is this useful in a network security perspective? Now, when you get attacked, there is a tendency for you to find the source of the attack. Now, once you have the IP address of the source, after like digging into the attack and doing your research on what's going on, and then you will go into a public database. This is when a Whois database will come in handy because it will give us the basic information that we need, like who is the person or who is the group and what are their contacts that are responsible for this resource. And then we can try to contact them, tell them about the issue, and then we can try to resolve them together. Okay, so that's why it's necessary that you keep the Whois database entries updated at all times, because it is a very good resource for all of us in the network field as well. That is the end of our discussion. Thank you very much for joining us. If you have any questions, please feel free to send us an email at training, in our email address. Basically, it's training@apnic.net. Thank you very much again for joining us in this class. And for other e-learning courses, you can go to our website at training.apnic.net. And most of the videos will also be uploaded onto our YouTube channel at youtube.com/apnictraining. Thanks again for joining us, and we hope to see you in other e-learning courses. Bye!